when you have followed my YouTube channel, you could see that I was working on a square wave oscillator, working between approximately 30 Hertz and approximately 40 kilohertz, but important to tell that with this setup you have to choose for the frequency band that you want to use. So it's not a, say, completely coverage square wave oscillator for all these frequencies, but you can surely find out the frequencies that you want to use, want to have, etc., etc. So this is that circuit, and now it is the second video about that oscillator. Well, there's not so much more to tell. This is of course looking as a quite sloppy circuit, but it is not. That's also important in a certain way. Here are a few switches, and I will tell more about it later. The most important thing to tell is compared to the original schematic, and this is that original schematic. I have, say, changed the value of one resistor. Only that one gave, say, better properties. Changing the value of that one resistor has given out better properties, especially about the restarting of the oscillator. So it was in the earlier schematic 43K, now it is 100K. And I was, say, in the past thinking about why does this oscillator suddenly stops and stop. When I was switching through these two capacitor banks, and most important thing to conclude was that when these two switches, switch 1A and switch 1B, are hanging between these two capacitors, and also here because they are completely coupled to get a good waveform, and with good I mean that the duty cycle is the same. Anyway, the duty cycle is of course the same when the capacitors are exactly the same and the whole circuit is the same, and that was the idea of this video and this circuit. So when they hang here, sometimes, or say more or less always, the oscillator does not want to start again. So let me demonstrate that. Perhaps it's interesting to show. So, and here we have a certain frequency out, and I want to tell later about these two circuits that I've made. One is an indicator that the oscillator oscillates or not, and one is a very tiny simple audio amplifier that could be useful. And of course when you don't need it, make a switch to switch that audio out. So I'm now on the lowest frequencies here, and you can surely hear that we are now on a higher frequency. On the oscilloscope we can see it very, very properly. The waveform is, by the way, very pure, completely pure. And say the next thing that I'm going to do with this oscillator circuit is to make here a pulse ratio that differs. Say I want to make needle pulses, and they are very useful when you want to make oscillator circuits, and especially transistor oscillator circuits that drive a coil for a high voltage. Anyway, this voltage is of course, this frequency is of course quite low. And I have by purpose made this audio amplifier as tiny as it is possible, because you don't want to be hindered on your workbench when you are doing, say, experiments with different frequencies, say different frequencies to drive a transistor or whatever. So that was all. And here you see, or not here, the frequency that is generated at the moment. It's so high that you can't hear it. Anyway, the human ear is not perfect in many ways, by the way. Anyway, more on my YouTube channel. So let's go to say the frequencies where we can hear what happens. And let me at first show, say, the not so good property of this simple oscillator. And this is the frequency switch, and when that frequency switch hangs between two positions, the oscillation stops. You can see it and hear it, but when we bring that switch to the other better position, you can hear that it starts again, and see of course that it starts again. Say it's now 3000 Hertz or so, whatever. I have not connected my counter to this circuit, but anyway, well, what are the most important things to tell? Perhaps again, change this resistor to 100 kilo ohms. And furthermore, about the two other schematics that are also usable in the circuit, of course you can say, well, I don't use these circuits because I know I see on the oscilloscope what's happening, etc., etc. But on the other hand, it could be useful. So here is that red LED indicator. By the way, only a red LED works here. No other colors work here, and I have indicated here 4K7 and 470 ohms. It's a good idea to use here a small potentiometer in the order of 10 kilo ohms to set the, say, how that LED acts, burns, when the oscillator is working or not in a specific way. And by purpose, that's of course logical. I made this circuit in such a way that there is an enormous decoupling out of that LED indicator to the oscillator circuit. And the reason is that such a LED indicator can have an enormous influence on the waveform, and that's the reason why I have here connected this LED indicator to the top of the output potentiometer, but of course with an enormous resistance here, 1 mega ohm, and a small capacitor of 27 nanofarad. Of course I needed a capacitor because I did not want to, say, have any DC influence out of the oscillator. So this is a more or less, in a certain way, and also a kind of universal circuit. Say, to indicate AC voltage on a line where at the input there is an enormous high decoupling because of that resistor and that capacitor, etc., etc. So the second schematic is here. Very simple. One phase rectifier. Here is a smoothing capacitor. It serves only one transistor, and that one transistor has here a 570 nanofarad capacitor. It gives out that the frequencies are better reproduced, and here on the input of that tiny one transistor amplifier, of course no hi-fi or whatever, the only idea is that it can reproduce the sound out of the oscillator. Here's a 10 nanofarad capacitor, and it goes to this location here. Thanks for watching. My camera runs out. I only have, say, 30 seconds or so. Perhaps it's still interesting to show what is happening in this circuit. And well, till everything stops automatically by my camera, etc. Here is that oscillator again. And here are the waveforms. They are always very interesting. Waveforms are very, very pure, and I have done everything to keep the waveforms as pure as possible. And I will try to cure this part here. And of course, perhaps you can hear on the background the sound that is, say, given out via that one transistor amplifier. That is very, very loosely coupled to this oscillator, and of course when it's not loosely coupled, the oscillator can stop, will stop, etc. etc. Thanks for watching.